All right, we are ready to go. So today we're going to finish up chapter 14, heat transfer methods. Essentially, we're going to learn how heat moves from one place to another. It's fairly straightforward. We have three different methods for heat transfer: conduction, convection, and radiation. And you may have learned these at some point in your life, and they're pretty simple. Conduction of heat occurs when two things come in contact with each other. It can be two solids coming in contact with each other. It can be a liquid and a solid coming in contact with each other. It can be a liquid and a gas, or a solid and a gas. It doesn't matter. If they're in contact with each other and they transfer some heat energy one to the other in some way, then that's considered conduction. Then there's convection, where heat is transferred through a material because of movement of the material itself. So, for example, we have this room here, this little bedroom here, or not a bedroom, a couch room, whatever it is. Anyway, this room here. And we have windows that are not perfectly sealed shut, doors that are not perfectly sealed shut. And sometimes we even have a fireplace that has a vent behind it on purpose. Mine has a vent behind it for this purpose. And that means that the hot air that you're creating in the fireplace, which rises up the chimney, will be replaced by the cool air coming in from all these different places that it can come in from around the windows, through the doors, through vents, or whatever else. And that is called convection. And the reason that it is moving is because the heating is creating this air that is less dense, that rises up the chimney, and that creates a void, it creates a vacuum, essentially, a low pressure region here. And this high pressure air moves into that low pressure region. And that's usually how it works. You have one part of the fluid or the gas. It can even work in solids. One part of this that gets warm and then moves for some reason, usually rises or moves in some way, and something cooler moves in to take its place, right? So you're right that this seems like it would make things cold in here, but you're forgetting that there's a third type of heat, which is what we call radiation, right? So, and there's also, between the chimney and the house itself, there is conduction of heat because the chimney gets warm. So as the chimney gets warm, you get conduction of heat into the walls and everything else, and that heats your house as well. Also, though, you have this radiation coming out of the fire. Radiation is light. Now, light comes in many, many different colors, but it also comes in things that aren't even colored, like infrared and ultraviolet and other forms of light that are outside what we can see. But all those forms of light can be absorbed by objects, can be absorbed by materials, matter. And when they get absorbed by matter, that energy from that radiation, the energy from that light, is also absorbed by that matter. And oftentimes, most of the time, it gets re-emitted. Some of that energy can heat up the material, can heat up the person or the couch or the wall or whatever. Some of it gets re-emitted as new radiation. That's what gives the couch color. You know, that radiation comes from the couch giving off radiation from the energy it has received and the energy that it already has. And some of it is given off in invisible radiation, like infrared radiation and other types of radiation, which can go off and heat other things, like the air. The air around us is easily heated by infrared light. And so infrared light that's given off by anything that's giving off radiation is heating up the air. So the air gets heated by this radiation as well. And some of the radiation coming directly off the fire is actually infrared radiation. So some of the radiation coming off the fire directly heats the air, right? There is a little bit of convection that comes out of a fireplace because not all of the hot air in a fireplace goes up the chimney. Some of it actually comes out the front. You generally don't want that because usually when you do get that, you get a little bit of soot or ash in your house, smoke, in other words, and that's usually not something you want. You don't want those fumes and those ashes and things in your house. So generally what you do is you try to prevent that. And in some cases, fireplaces don't have any gases coming out. They seal it up, like in the case of an iron stove. They seal up the fireplace and only allow the radiation to come out the front, and then the whole stove gets hot, and it heats the room by conduction. It is in direct contact with the air of the room or the walls of the room or whatever, and heats the room by conduction. So we have these three different heat transfer methods: conduction, convection, radiation, and usually where you find one, you'll find the others as well. It's very common to find multiple methods of heat conduction or heat transfer. But it's not always the case. You don't always find all three. So one of the things that we do in houses, in machines, and other things to prevent some of these heat transfer methods is we insulate. Right? We use materials where heat does not transfer through very easily. That's what we do in walls with fiberglass insulation or cellulose insulation. Most houses have fiberglass insulation in the walls and cellulose insulation in the ceilings. Cellulose is essentially just paper. Paper makes a great insulator, and we do this to prevent that heat from leaving the house or from entering the house, one way or the other. In the winter, we prevent it from leaving the house, and in the summer, we prevent that heat from entering the house, right? And the speed at which, or the rate that heat leaves or enters, is dependent pretty much on two things: what it has to go through, what material. Well, it's dependent on three things. It's dependent on what it has to go through, what material it has to travel through, what amount of material it has to travel through, the thickness of the material that it has to travel through, the distance, and then also the temperature difference between the cold side and the hot side. Those three things are the things that determine how fast heat will flow, or in other words, how much heat will flow through a particular surface. And it really comes down to heating up that surface. So if you can avoid having a surface that gets hot on one side and cold on the other side, if you have some kind of transition zone in here where the outside, the way outside that's way over here may be hot, but by the time you get onto the inside that you care about, it's cool, or vice versa, then you're in a really good place. And this is why houses, buildings, machinery that gets hot, other things, do not have a single piece of material here. They don't just have this one piece of thin material, because if it's a thin material, then you've taken away one of those factors, the thickness of the material, the distance between the sides of the material, so that the distance between the sides is very, very small, and hot molecules or hot atoms over here can almost directly affect cold atoms over here, or vice versa, and heat will flow from hot to cold. So if you're in the middle of building your house like I am, I have some walls in my house that are just a piece of plywood at this point. I haven't quite insulated them all yet. I need to get that done this week. But if you walk up to the wall right now and put your hands on the wall on the inside, it's really cold. That wall is really, really, really cold. And that's because heat, the difference in distance between outside and inside is only 7/16 of an inch. And the heat is being allowed to flow out of the house into the outside, into the garage in this case. And so that wall is really cold on this side when it shouldn't be. But if you touch a wall next to it that has 7/16 plywood, and then it has 6 inches of fiberglass insulation, and then it has sheetrock on the inside, then you touch that sheetrock on the inside and it feels just the same temperature as the room you're in. But if you go into the garage on the other side and touch the plywood on the other side, it's very cold. So we've created this distance between the cold side and the warm side, and we've put material in between that don't conduct the heat very, very rapidly. That's a very poor conductor of heat. by creating that gap of those materials. Another thing that is associated with this is the amount of area, the cross-sectional area, but that hopefully should be obvious. A very large wall will have more space to conduct heat through it than a very, very small wall. But area does make a difference. So, for example, when you're building a house and you're going to get it approved by the city planners, the city people who give you the permits for houses, they want all the houses to be energy efficient. And so if you have too many windows, they will either put taxes on your house, or they will tell you to take out some of the windows. Now the reason for that is because windows are not very good insulators. They have double pane windows and triple pane windows, which make them better insulators, but even the best insulating window is worse than the worst insulating wall. They're just not very good. So if you make your windows smaller in area, less heat can get through them. That's one option that you have. Or if you just reduce the number of windows, that reduces the area of the windows. And that is also helpful. So this ends up being the equation for how heat is conducted through a wall. This is going to be, we're going to talk about heat transfer rate, so the rate of heat conduction. So you have Q over T, Q being the amount of heat or the amount of energy in form of thermal energy, divided by the time. So heat per time is equal to the area. So if the area gets bigger, the amount of heat going through gets bigger. If the temperature difference gets bigger, the amount of heat going through gets bigger, right? But if the distance gets bigger, if the thickness of the wall, in other words, gets bigger, then the heat transfer goes down, actually. So that's an inverse relationship there. And then they have this K thing in here, which is the thermal conductivity, which is related to the material that is used in the insulation or in the wall or whatever. And of course we have a table of all these different thermal conductivity constants. And you can see here that for metals, silver, copper, gold, aluminum, steel, stainless steel, it's fairly high. I mean, stainless steel is the lowest of them, but you have, all these other ones that are up in the hundreds, right? Iron is, 80. But this means that the heat travels through them extremely easily, extremely quickly, okay? And that's great if you want to have a copper pot or a silver pot or a gold pot, so that you heat the bottom of the pot and the sides of the pot get warm too, right? Aluminum, get the same kind of effect. Not as much, but just a pretty good effect like that. So if you want heat to travel easily, you make things out of metals. But if you want this thing to be metal but not heat to travel easily on it, you use stainless steel, right? And this is also used in cooking all the time. So if you want something to get really, really hot on the bottom of the pan where it's in direct contact with the heat from the stove, but you don't want the sides to get hot, then you make it out of iron or stainless steel. And stainless steel pans are used like that all the time, so that the sides don't get very hot, but the bottom does. And then oftentimes you have pots made of all kinds of things, made of copper, made of aluminum, made of cast iron, whatever, but the handle will be stainless steel. So that you can grab the handle even if the pot is hot, because heat does not travel up the handle very easily. So it's a very useful thing. More likely, you'll find a handle made of what? See if we have a nice... We don't have one here. More likely, you're going to have a handle made of glass, which is much more like... plastic, which is much more like glass in its heat conductivity. Plastic does not transfer heat very well at all. It's actually more like asbestos, or maybe even wood is what plastic is like. So it does not transfer heat very well at all. It has this very, very low heat conductivity, and plastic allows you to, the plastic handle allows you to handle a hot pot without worrying about it at all. The downside to plastic, of course, is that it has, many plastics have a fairly low melting point. And so if you're not careful, you can melt plastics in the kitchen. They're getting better at using plastics that can resist higher temperatures, but it's still a bit of a problem. You can see here that these lower numbers here, styrofoam, air is a fairly low number in heat conductivity. Down feathers, we could just insulate our house in down feathers, right? In fact, down feathers are a great insulator because air is a great insulator. What down feathers do is it gives you a great big pocket of air that things have trouble traveling through, okay? And that's what styrofoam does too. Styrofoam is mostly bubbles of air with plastic, made with plastic, right? Glass wool, which is fiberglass, is the same idea. Most fiberglass insulation is like 90% air, and it's just got a bunch of glass kind of in there. So one of the best things that you can do for insulating something is to fill it with air, but fill it with something else in the air to prevent the air from moving very much. Because if the air can move from one side of the other to a boundary, then it can transfer heat through convection, right, instead of conduction. But if you put down feathers in there to prevent the air from moving around too much, or if you put wool in there, like or glass wool, then you can prevent the air from moving around and keep your home very warm. Cotton works very well as well. In fact, one of the most popular forms of insulation these days is made from old blue jeans and old cotton clothing. In fact, old clothing of all kinds. They grind it up into this kind of fluffy, woolly stuff, and then you just put it in your walls. It's also one of the most expensive ones. I don't know why, since it's recycled, but it is. Maybe because it sounds cool. I don't know. Recycled things can be expensive. Okay, so anyway, let's take a look at conduction rate through an ice box. We have a styrofoam ice box. So styrofoam has this heat conduction, this heat conductivity with a thermal conductivity of 0.010, pretty good. It's one of the lowest ones here. It is the lowest one here, in fact, styrofoam. If you could, and a lot of houses now are actually almost completely covered in styrofoam. That's not uncommon. It's wrapped around the outside, it's wrapped around the inside. The foundation is made of styrofoam filled with concrete. That's very common these days. So we have a styrofoam box that has a total area of 0.950 meters squared. The walls have an average thickness of 2.5 centimeters. The box contains ice, water, and canned beverages at 0 degrees. The inside of the box is kept cold by melting ice. How much ice melts in one day if the ice box is kept in the trunk of a car at 35 degrees Celsius? So what do we have to ask ourselves at this point? We have to ask ourselves what kind of heat is flowing, right? We have a temperature difference, and what kind of heat is going to be flowing. We know the area, we know the distance, which is the thickness. We also know the inside temperature and the outside temperature. We know how much time is going to go by, and we want to know Q, essentially, right? We want to know how much heat is going to be transferred through this. So we plug all those numbers into here that we know, and that includes the time. The time gets put in here as well at the end here. So they plug in all the numbers, and then they plug in the time, and they get 1.15 times 10 to the 6 joules. 1,000,000 joules of energy is going to enter this box and melt ice during this time. So if we're going to use that amount of energy, we use the latent heat of fusion for ice equation with that amount of energy in it, 1.15 times 10 to the 6 joules, the latent heat of fusion for ice, and then we solve for the amount of ice that gets melted, 3.44 kilograms. Now every year on my birthday, January 1st, I have a great big, well, actually I have it on I usually have it on December 31st, and then it ends sometime around the 1st. But every year I have a big party that involves mostly a bunch of cheese. And I order this cheese from a company that imports it from all over the world, and they ship it overnight in a container full of ice. And it's quite important that they know these kinds of things, because this is coming from a fair distance away, has to travel sometimes in warm buildings, and they actually have charts of these things in these shipping companies that send things with ice. It's more important in medical companies where we definitely have to keep things certain temperatures. So every 8 weeks I actually get a shipment of a biological injection that I have to take for my old broken down system. And that biological injection has to be kept at a certain temperature, below a certain temperature and above a certain temperature. So it has to be kept in a certain temperature range. And they have charts in these companies that do this kind of shipping that say you're shipping this distance, you're shipping at this time of year. They've taken into account temperature differences. They've taken into account the mass of the object in the box. They've taken into account the thickness of the styrofoam of the box, all that stuff. And they've given these shipping companies, from this equation, they've given these shipping companies the amount of ice that they should put in the box. And then they always put a little bit extra. Okay? So it's very practical. So here's, let's do conduction through an aluminum pan. This time, they're going to tell us that water is boiling on this electrical element. And the saucepan has a thickness of 0.8 centimeters, and it's 14 centimeters in diameter. That's going to help us to figure out the area. And the boiling water is evaporating at a rate of 1.0 grams per second. So they're telling us an evaporation rate now. So that's a little bit different than we've seen before. They want to know what the temperature difference is through the bottom of the pan. So immediately we're going to solve our equation for the temperature difference, and we need to figure out, we know the distance, we know the thickness through the pan, we know the cross-sectional area at the bottom of the pan, we know the K of aluminum, but we don't know Q over T. We haven't been given Q over T. We've been given grams per second, which is how much water is evaporating per second, not how much heat is going in per second. So we need to figure out how much energy, heat energy, is required to evaporate 1 gram of water. Well, we can do that using the latent heat of vaporization equation, right? If we use the mass of water, which is 1 gram, and then we use the latent heat of vaporization, we'll know that 2,256 joules are required to evaporate 1 gram. So if we're doing that every second, then it's 2,256 joules per second being used to evaporate the water in there. Then we can plug that number into Q over T, which is exactly what they do. They plug that in the number for Q over T, then they solve this whole equation with all the stuff that we've got, and they find that there's 5.33 degrees Celsius temperature difference from the bottom of the pan to the top of the pan. Not much. The top of the pan is about the same temperature as the bottom of the pan, only 5 degrees difference. Now, why is the burner that is made of metal, why is the burner glowing red hot, but the pan is not glowing red hot? Here's your question of the day. Remember, why does temperature do different things to different materials? Specific heat, right? Some materials, as they raise up in their temperature, their specific heat is different than other materials, and so one of them will raise higher up in temperature while the other one won't raise as much in temperature. But even if they're at the same temperature, they have a different thing associated with their specific heat. What's the thing that's associated with their specific heat? And also their latent heat. Water, for example, when it reaches 100 degrees Celsius, what happens to water? It boils, right? And you have to keep putting energy into it, keep boiling. But what happens to aluminum when it hits 100 degrees Celsius? Nothing special, right? You have to wait till it gets to 2,000 before it starts melting, right? So different materials encounter their phase changes at different places, right? And it just so happens that the material that the stove element is made of, which is usually some kind of chromium, happens to glow at the temperature that it's at. That's just one of the properties of it. Most metals will glow at some temperature. This one happens to glow at that temperature. Okay? But aluminum doesn't happen to glow at that temperature. Okay? Nor does steel, it's a different kind of thing. So it's just different materials is what it is. Water, of course, when you put all that energy into water, it takes a lot of energy to boil water. So it's going to pull a lot of energy away from the aluminum, even at that temperature. So you can actually boil water in a styrofoam cup or a plastic cup over a fire. Yep, you can do that. And why is it that you can do that? It's because the water in the cup, right? You still the styrofoam will melt at those temperatures, but since the heat is transferring out of the styrofoam so quickly into the water, because the water is present, because when the water and the styrofoam are in contact with each other, they're pretty much like one thing. So as the styrofoam heats up, it transfers heat into the water. Now that only works for cups that are fairly thin walls. If you have a very thick wall, then the heat won't get through to the water quick enough, and you'll melt your styrofoam to a point. Eventually, it'll get thin enough that you'll get your heat through. But if you have a very thin styrofoam barrier-like cup, then you can do that. So it becomes quite interesting. There's a lot of things involved here, and not all of them are related to everything. So that's important to remember. So that's conduction. Convection, as I've mentioned before, is this movement of a fluid. We usually talk about air when we talk about convection. Like in this house here, you have this. We have this furnace here, which is essentially heating air. The hot air is rising above it and pushing cold air from the ceiling down to the bottom of the room, and then that cold air gets heated and pushed up to the top again, or gets rises to the top, and you just get this convection circulation thing going. You have to remember that when you're doing a system like that, you have to have a place for the flue gases to go, because when you're burning something, some of those gases are poisonous to life, so you got to get rid of them. But it also happens in water. As you boil water, or as you heat up water, the warmer water gets less dense and it rises to the top, and the cooler water falls down, and it has this convection thing going on. Some ovens are designed specifically to create this effect. Some ovens are designed with fans inside of them to make the air move more. The air will move naturally within an oven, but when you put things in the oven, it impedes the airflow like a big pan. And so you've maybe noticed that when you bake cookies, some of your cookies are more baked than others sometimes, and that's because the distribution of the hot air is not necessarily even throughout the oven, so you don't get an even convection heating throughout the oven. If you go to an industrial oven in a bakery, for example, or a pizza restaurant, well, not so much a pizza restaurant, like a bakery that bakes bread, bread is baked almost completely by convection, by the movement of hot air around the bread. That's really important for baking bread. And so they put fans in their ovens. And their ovens are extremely expensive for that reason, because it's hard to have a moving electrical thing inside of an oven that can go up to 800 degrees, because it almost always will destroy that moving electrical thing. So they have to figure out a way to insulate things and to protect things and to make things out of materials that can handle the heat, and I mean, the difference between a normal oven and a convection oven is almost twice the cost, even in a normal kind of home environment. The convection oven for your home will cost thousands compared to hundreds for a normal oven. So they don't really give us any equations for convection, because the equations for convection are actually extremely advanced. They have an entire class on this in physics and another one in engineering that is just learning how to do these equations. In some schools you have 2 classes that you have to take. But we can do a little bit of stuff. For example, we can use our specific heat equation to talk about how temperature changes due to convective heating, and then talk about heat flow as this amount of heat that we calculated from the change in temperature divided by time. So if the temperature changes a certain amount because of heat flow through a wall, for example, from convection, or through a ceiling or whatever else, then you can calculate the amount of heat that flowed to change the temperature, and then divide it by the amount of time it took, and then you'll be there. And that's exactly what they do here. Now, the first thing one of the things that they also do is they calculate the mass of the air in the house from the volume of the house times the density of air, and then they use that heat specific heat equation to calculate that, and then they divide by the time. But besides that, it's there's nothing new here that we're doing. We're just applying these things in a specific situation, applying the specific heat equation in this situation where the heat flows through a wall or through a ceiling or through the air or something. But to actually calculate how that works through the air is extremely difficult. But this has a lot to do with also things that we're very familiar with, for example, wind chill, right? So wind chill is due to convective cooling rather than convecting heating. You could think of it as your body convectively cooling the air outside is what is wind chill. But what happens is as your body is in an area where the air is not moving, it just cools by direct conduction of heat and radiation out of heat from your body. So you have heat leaving your body at just kind of normal rates. But when wind moves past it, your body is constantly coming in contact with new cold air. When wind is not there, you kind of create this little this barrier of warm air around your body. And you really notice it when you put on a jacket. When you put on a jacket, you definitely create a barrier of warm air between yourself and the outside air. And that barrier of warm air kind of keeps you insulated, keeps you warm. But even without a jacket, you create that. And the hairs on our body create that and everything else. That's why you get goosebumps. It's a natural reaction to create an insulative barrier. Those hairs raise up and they prevent the air from moving too much around your body, so you can keep it warm. In earlier times we were hairier people. People that have less hair on their bodies generally probably have ancestry that comes from warmer climates. People who have more hair on their bodies generally have ancestry that come from colder climates. But anyway, this convective cooling happens when the wind comes by and takes that barrier of air away from you and replaces it with cold air, and then your body has to heat that up again, right? And this is the wind chill table. You have these wind chill tables. So the degrees Celsius is up here, and then there's also degrees Celsius down here. And this one tells you, this one tells you wind speed. This one tells you degrees Celsius. So this is the temperature of the air outside. This is the wind speed of the air out here. And this will tell you what it feels like. Like this is your wind chill right here. So if you've got 10-mile-an-hour wind and it's 0 degrees, then it feels like negative 15, right? So that's your wind chill. And here is this is how fur works, right? Fur works by you have the body down here that's warm. You have the fur in between you and the air. It's very, very cold out here. These convective loops form. This is that barrier of air that's formed. Your body warms up the air and it rises away from your body. But then as it gets to the cool part out here, it gets cooled and it falls back to your body. So it never gets really very cold. It just stays going in this loop. Gets warm, gets cooled, gets warm, gets cooled. But it never gets as cold as it is out here. So it creates this nice little barrier. And the reason that we get goosebumps is to stand this hair up to make it a thicker barrier when it's cold, right? That is the purpose of the goosebumps thing, to create that convective cooling. We'll come back to that in a minute. So the flow of mass during convection, the sweat heat transfer away from the body. So also sweat can contribute to this, because as you're going through this convective process here, you have not just like nitrogen in here, which is mostly what air is, but you also have liquid or water vapor, which is gaseous water, right? And if it gets too close to here, or if it spends too much time down here and gets really, really warm and then rises too quickly up here, it will actually kind of penetrate the barrier and then it will condense. And then all of a sudden you're sweaty, right? So if it gets too cool, if there's too much temperature difference between your outside your body and the inside your body, then that water vapor leaving your body condenses as it goes from that too warm to too cold, condenses, becomes liquid, sticks to your body or sticks to your hair or sticks to whatever. And then all of a sudden you have this layer of liquid on you. Well, liquid, as it evaporates, takes energy, and it takes energy not only from the air but from your body. And so it cools you off. Now that's nice on a nice summer day. Not so nice on a cold day. If you get liquid on you and it evaporates from your skin, you get really, really cold, right? then your skin is definitely warm enough to make a thin layer of water evaporate. So that's why you don't ever want to have water near your skin when you're in the cold. And this is one of the reasons that they talk about layers of clothing. Your first layer of clothing should be snug on your body, and it should be made of something that will suck moisture from your skin. Cotton does not do that very well. Cotton does it fairly well, but the problem with cotton is that it holds the moisture better than most. It soaks up the moisture and then it doesn't evaporate it out. So it'll soak up the moisture and it will freeze. Cotton will actually freeze because it's an organic, because it's a natural fiber that freezes anyway. However, polyesters, which are an organic fiber that are not very natural, they work much better at pulling that through the fabric and then allowing it to evaporate off of the fabric very quickly instead of off of your skin. So your first layer should always be some kind of polypropylene, polyester type fabric. Another fabric that works quite well is silk. Silk does a good job of that, but it's very similar to polypropylene. So then you play it where other layers outside of that are meant to trap all that convective air stuff. But that first layer should be wicking that moisture off of your body so that it's not sitting on your skin and making you clammy and cold when it's cold outside. Of course, a lot of in athletics, there's a big thing about this wicking and moisture thing, and it has nothing to do with performance. It has everything to do with we don't want our athletes to look sweaty all the time. Having the sweat on your skin when you're a performance athlete, especially when you're overheating, is extremely important. It's extremely important to have that contact of your skin with your sweat because it cools your body down. If the internal parts of your body get overheated, your performance goes way down. Your ability to perform, your efficiency of using energy and everything, really, all your performance goes down as your internal heat goes up. So it's very important to cool off. One of the things that most athletes understand is that when you're done with your performance is to cool down a lot. Cool down drinking fluids, cool down with ice, cool down by going into a cool room. You never get into a hot tub or a sauna after you work out because that's really just going to cause damage to your body. You want to cool things down, let things return to normal. So here we're going to talk about that sweat heat transfer away from the body. Again, it's going to have something to do with this equation, this heat flow equation, but instead of having the conduction thing on one side, we have now latent heat of vaporization because sweat evaporates from the body. So the latent heat of vaporization is our Q, and then we divide by time. Mass times LV over T, and we want to know how much mass per time, so we solve this for mass over T by dividing each side by the latent heat of vaporization. Our amount of energy is 120 watts, which is 120 joules per second, divided by the latent heat of vaporization, and you get 2.96 grams per minute of sweat lost. Right? And people often think this is the way you lose weight. 2.9 grams at 120 watts? That's not very much. And all the weight you're going to lose is water. That's not what you want to lose in your body. You have to drink it back. Your body has to have the same amount of water in it all the time. So if you're sweating, you have to drink. So losing weight has nothing to do with sweating. Where do you lose weight? Where does the weight go if you're losing weight? Where does the mass go? Can't convert mass into energy in your body. Absolutely impossible. Fat is fat. Can't do anything about it. You can burn fat, you can break bonds in fat, but that doesn't change the mass. All the molecules are still there in your body. Where does it go? What are most of the molecules in your body made up of? Does anybody know? They're made up of carbons, hydrogens, oxygens, things like this.
Wait a minute. Is it from the respiration?
We breathe in every day oxygen and nitrogen, but the only thing we keep is the oxygen. We breathe out every day, and what do we breathe out? carbon dioxide, which is like an oxygen with a carbon on it. It's the same thing that we breathe in, except we attach a carbon to it when we breathe it out. That's where all the weight goes. It's in our exhalation every day. As we exhale, some of it does go out in the form of water in our breath as well. There is some water that we breathe out that is formed in our body in the respiration cycle. So it's also water, but carbon dioxide is the biggie. As we breathe out, this is how you lose weight, is by breathing out. So when people say, well, I'm just going to lose weight just by doing this miracle thing or this miracle thing, this special diet or this whatever else, it's all lies. There's only one way to lose weight. Exercise. Because exercising is the only thing that makes you breathe more. The more you breathe, the more you lose weight. That's what it comes down to. When you're exercising, you breathe 5 times faster than when you're just sitting around. You can't sit around and lose weight. Can't happen. You can starve yourself, but you'd die. You just can't do it any other way. The only way to do it, really. And I know this because just last year I lost 30 pounds in 2 months by starving myself because I was so sick I couldn't eat. And so I was literally just dying, and it's an unpleasant experience. The only way to lose weight quickly is either to starve yourself and be sick and die, or to exercise. You have to exercise. And you should not eat any more when you're exercising. You should eat the same amounts and exercise, or maybe a little bit less than exercise. But exercising is the key because all that weight goes out in your breath. As you breathe more and more and more, you're getting rid of more and more carbon. All those fat molecules and everything in your body, they're all made of carbons. They're big chains of carbons. A bunch of hydrogens on there too. We get rid of those too. But hydrogens are small compared to carbons. So we got to get rid of carbons. Anyway. Now, the last one, radiation. My favorite thing to talk about with radiation, let's see if we can find it. Is campfires. How many of you have been on a camp out with a fire? So the radiation from a campfire, right? When you're sitting at a campfire, let's see what's the best picture. Here we go. Here we have a guy roasting his marshmallows, right? Now, if you've ever roasted marshmallows on a campfire, you know that you can hold them directly above the fire. But what almost always happens if you hold them directly above the fire? They torch, they get burned, right? So the best thing to do is to either hold them on the side of the fire or to wait till it dies down and there's nothing but coals, these glowing coals, and then roast it slowly there. So why is there such a difference? Well, fire has 3 methods of heating things. The first is by conduction, where it actually touches something, right? So if you stick your hand in the fire, you can actually burn yourself by directly touching the hot things that are in the fire. Okay? But then you have the convection. As things burn in the fire, they create these hot gases that float upwards. And those hot gases can heat things by conduction. But that convection of the rising hot gases is another heating method. And the third one is radiation. The radiation from the light coming from the fire. Now the radiation is what you feel when you're standing next to the fire. Because the convection goes up, the conduction is in the fire, and the radiation goes in every direction. So when you're just standing there holding your hands out, the radiation is what you're feeling. Now what happens if you are 1 meter away from the fire and you're comfy, and then you move twice as far away? 2 meters. You're definitely not comfy anymore, right? There's a huge difference with distance when it comes to radiation. And that's because this amount of radiation is a fixed amount of radiation. It's a certain amount, and it spreads out as the area spreads out. And if you go out twice as far, you get not twice as much area, you get 4 times as much area. So it drops off as 1 over the distance squared. Just like with regular light. For example, if I hold this piece of paper up in front of the projector here, at about 1 meter. Here's 1 meter-ish. If I hold this piece of paper up, it covers about 1/4 of the screen. See that? At 1 meter. If I bring it into a 1/2 meter, it covers the whole screen. A quarter drop. Yeah, it's twice the distance, 1/4 of the area. Right? So if this was heating my hand, right here I'd get, and you can feel the heat here. Right? Let's say I'm getting 10 joules here. If I move it to here, twice as far away, how many joules am I getting now? 1/4 the amount of 10, 2.5. Right? So it's not just a matter of, move it twice as far, you get half as much. You move it twice as far, you get 1/4 as much. Right? So radiation is an interesting thing because of that whole distance thing. Radiation is also interesting because it does not require a medium to travel in. It can travel through things. It can travel through a medium. What has to happen to my screen?